Whenever possible, you should double-check the results of an engineering analysis using an alternate analysis approach. This video presents an easy way to check the calculated response of a first-order circuit using the differential equation governing the circuit. First, I'll review how we determine the response of an RC circuit. An RC circuit has one energy storage element, a capacitor, connected to a network of sources and resistors. Thevenin's theorem says that any circuit of this kind can be represented as a voltage source in series with a resistor connected to the capacitor. The voltage source is the capacitor's open circuit voltage. It's the voltage across the capacitor if the capacitor is replaced with an open circuit. The resistance in this circuit is the Thevenin resistance seen by the capacitor. The response of the capacitor voltage for time greater than 0 has this form. In this equation, V0 is the initial voltage across the capacitor just after this switch closes. Since capacitor voltages can't change instantly, this voltage is the same as the capacitor voltage for time just less than 0. This circuit is a model for time greater than 0, so we can't determine this initial condition from this circuit. We need to determine V0 from a circuit that's appropriate at time less than 0. The open circuit voltage, VOC, is the capacitor voltage as time goes to infinity. If the input's a constant, the capacitor voltage will eventually become a constant. The capacitor behaves like an open circuit, and the capacitor voltage is identical to the Thevenin open circuit voltage. Finally, the time constant is equal to the Thevenin resistance seen by the capacitor times the capacitance. We've also talked about RL circuits. The response of an RL circuit is very similar to an RC circuit, except that voltages and currents change roles. The inductor in an RL circuit is connected to a network of sources and resistors. Norton's theorem says that any circuit of this kind can be represented as a current source in parallel with a resistor connected to the inductor. The current source is the inductor's short circuit current. It's the current through the inductor if the inductor acts like a short circuit. The resistance in this circuit is the Thevenin resistance seen by the inductor. The response of the inductor current for time greater than 0 has this form. In this equation, I0 is the initial current through the inductor just after this switch closes. As with RC circuits, the initial condition is not necessarily determined from the circuit shown here, since this is a property of the inductor just before this model becomes appropriate. The short circuit current, ISC, is the inductor current as time goes to infinity. For a constant input, the inductor current will eventually become a constant, the inductor will behave like a short circuit, and the inductor current is the same as the short circuit current. Finally, as we've already seen, the time constant is equal to the inductance divided by the Thevenin equivalent resistance seen by the inductor. The equations governing the response of both RL and RC circuits to constant inputs can be written in this form, and the response of the circuits is simply the solution to this differential equation. With the differential equation written in this form, the time constant and the steady state response are readily determined directly from the coefficients of the differential equation. The solution to this differential equation with this initial condition has this form. Y0 is the initial condition and tau is the time constant. YF is the value of y as time goes to infinity, which is the particular solution to the differential equation. Solving this differential equation is the same as determining the response to the corresponding RL or RC circuit. This means that we have some ability to double check our analysis of first-order circuits. We can determine the circuit response as we did in the previous video by solving 3 different independent problems to obtain the time constant, the response as time goes to infinity, and the initial condition. Alternately, we can write the differential equation governing the circuit and determine the time constant and the steady state response directly from the differential equation. This gives us an alternate way to determine those 2 values, which can be a valuable way to check our results. We don't have an independent verification for the initial condition. The initial condition is a separate piece of information from the differential equation and can't be inferred from the differential equation itself. This example is from our previous video. The switch moves from position A to position B at time t equals 0. We wanted to find the capacitor voltage, V of t, as a function of time for time greater than 0. We determined the solution by identifying the circuit as a first-order linear circuit with a constant input. For that type of circuit, we know the form of the solution, and we solved 3 separate problems to get the steady-state voltage, the initial condition, and the time constant necessary to write that solution. This was the solution we determined. When possible, we want to be able to cross-check our results. Writing the differential equation governing the circuit for time greater than 0 and determining the time constant and the steady-state response from the differential equation can provide that cross-check. If the values from the differential equation agree with this function, we can be pretty sure that we've done the problem correctly. Next, I'll write the differential equation for the circuit and perform that cross-check. This is our original circuit. To determine the differential equation for time greater than 0, we'll use the circuit for time greater than 0, which means that the switch is at position B. This is the circuit for time greater than 0. To write the differential equation governing this circuit, I want to label the capacitor voltage, which is already labeled as V of t, and then label the current, which is 2 farads times dV by dt. Now if I label this as node A and do KCL at A, summing the currents leaving the node, I get VA minus 12 over 4 ohms. VA is just V of t, so this is V of t minus 12 volts over 4 ohms, plus this current, which is already labeled as 2 dV dt, plus the current through the 12 ohm resistor, which is just V of t over 12. That equals 0. Now if I multiply this through by 12 to clear the denominators, I get 3 V of t minus 36 volts plus 2 times 12, which is 24 dV of t by dt, plus V of t is equal to 0. There's my differential equation. To put it in standard form, I need to divide out this 24. So I get dV of t by dt plus, this is 3 plus 1, 4 V of t over 24 is 1 over 6 V of t. Taking the 36 to the other side and divided by 24, I get 36 over 24, which is 3/2. So my differential equation is dV of t by dt plus 1 over 6 V of t is equal to 3 over 2. From this differential equation, we can check the steady state response and the time constant. I'll do that next. Now let's use that differential equation to cross-check our previous results. This was the response we calculated from the previous video. This is the differential equation we just determined for that same circuit. From this response, the time constant is 6 seconds. From this differential equation, the time constant is also 6 seconds. From this solution, the response as time goes to infinity is 9 volts. E to the minus infinity over 6 is 0, and V of infinity is just 9. From this equation, the final value is going to be a constant. If that's a constant, this term goes to 0, and V of infinity is 6 times 3 over 2, or 9 volts. The time constant and the steady state response is the same for both solutions, so we can be pretty confident that our solution is correct. This example is also from our previous video. The switch moves from position A to position B at time t equals 0, and we want to determine the inductor current, I of t, for time greater than 0. As with our previous example, we identified the circuit as a first-order linear circuit with a constant input. We then solved 3 separate problems to get the steady-state current, the initial condition, and the time constant. This was the solution we determined. Again, let's cross-check our result by writing the differential equation governing the inductor current. This is our original circuit. We want to determine the differential equation governing the inductor current for time greater than 0. To write the differential equation for time greater than 0, we need to analyze the circuit for time greater than 0. For times greater than 0, the switch is at position B, and the circuit we're going to analyze is this one. If I do KVL around this loop and call this voltage V6, I find that V6 is equal to this voltage, which is 2 di by dt, plus the voltage across the 12 ohm resistor, which is just 12 times I. Now, if I call this node A and do KCL at A, I have 3 amps going into the node. That's equal to the sum of the currents leaving the node. This current is equal to V6 over 6 ohms, so that's 1 over 6 ohms times this, which is 2 di by dt plus 12I, plus the current here, which is just I of t. So 3 is equal to 2 over 6, which is 1/3 di by dt, plus 12 over 6 is 2, plus 1 is 3I. Putting this in standard form, I multiply through by 3 so that di by dt plus 9I is equal to 9 amps. Let's use this differential equation to check our time constant and our steady state response from our previous solution. Now let's use the differential equation to cross-check our original results. This was the response that we calculated in the previous video. This is the differential equation we just determined for the same circuit. From this response, the time constant is 1 over 9 seconds. From the differential equation, the time constant is also 1 over 9 seconds. From this solution, the response of I as t goes to infinity is 1 amp, since this term becomes 0. From the differential equation, as time goes to infinity, I of t becomes a constant. This term goes away, and I at infinity is 9 over 9, or 1 amp. The time constant and the steady state response is the same in both solutions, and once again we can be confident that our solution is correct. So far, we've only solved for either an inductor current or a capacitor voltage in a circuit. However, we may need to find some other parameter in a circuit, such as a resistor's voltage or current. Next, we'll talk about using the inductor currents and capacitor voltages to determine other circuit parameters.